The basic principles of CPU design haven't changed much since 1836, the analytical engine, but they have been extended. Many new ideas get added. If you remember the photo we saw earlier in the course of how architecture evolves, it's like a building where people keep the foundations and they put extra stuff on and maybe they knock bits down and generally adding complexity all the time. So now, hopefully we have that basic understanding. We're going to look this week at some of the extensions that are used in more modern CPU design. So, there's an infinite number of possible features you might choose to add to a CPU. We can't study all of them. We're going to look at some of the most common ones. These include subroutines. That's roughly the ability to call a piece of code and come back. We'll look at what are called interrupt requests. That's a way to interrupt someone else's program and have your program come in. Typically, that's how an operating system will work, by continually interrupting things. We'll talk about different kinds of instructions. How do you design an instruction set? What design choices do you make? And in the afternoon, we'll look at ways of making CPUs go faster by pipelines and what's called out-of-order execution. This is a way to have the CPU do more than one thing at a time. It's a form of parallelism called instruction-level parallelism. And we'll finish the day by going back to design questions and resist versus risk debate. So the easiest of these extensions to deal with are subroutines. So these actually appeared late 1970s, at least. We talked last week about doing flow control, how to jump around in the program. Yeah, you can have special instructions like jump or conditional branch instructions. These are instructions that, depending on the state of what's going on, they might intervene and change the program counter to make you go to a different line of the code. Now, a more advanced version of that is the concept of a subroutine. You probably know subroutines by other names, and depending on the high-level language you're used to, you might know them by names like procedures, or functions, or methods. Most high-level languages will give you something like this. Roughly, it's the ability for your program to say, go and do this other thing, and come back when you've finished it. So you might be writing a video game, you're writing Space Invaders, the alien's been shot, and you say, go and deal with the alien being shot. Call a function called explode the alien, and that's going to take care of doing an animated explosion and making sound and giving you some points and clearing up the memory to get rid of where that alien used to be. Depending on the language, if you're writing in BASIC, you might call it a procedure. If you're writing in Lisp or Haskell, you might call it a function, and if you're writing an object-oriented program in Java or C++, you might call it a method. They're all variations on the same basic idea. Actually, can anyone define the difference between any of these concepts? What's the difference between a function and a method, really? So a function is technically a mathematical term. A function has the most rigorous definition. A function is when you go and do something, and everything it does is packaged together into a result. All the effects of a function come back to you in the form of a result. Whereas in a procedure, there's no returned result, but the procedure might actually do things. It might actually go and write to the screen or read something from a disk. Those are called side effects. The side effects is all the things that a program can do other than returning a final result. And a method is usually a combination of a function and a procedure that are packaged together inside of an object in an object-oriented language. At the level of architecture, they all run in pretty much the same way, and it looks like this. You're going to write your program. This is going to sit in memory, and you have these special instructions, usually called call, which tell you to go and call the subroutine. As we mentioned last week, we often try to use a separate word when we're talking about an architectural level from when we're talking about high-level languages. So we're going to use the word subroutine to mean things that exist architecturally, things that appear in the assembly language and machine code, whereas we're going to use words like these to describe the things that show up in your high-level language that get compiled into subroutines. So at the level of the machine code or the assembly, your program is sitting in memory and there are some special instructions called call, and in this case it's a square root subroutine. That's telling us we're going to do a form of a jump. We're going to stop executing here. We're going to nip down here for a while to this other part of memory, storing the square root subroutine. We're going to run that code. So far, that's like a jump that we saw last week. But the clever part is when we've finished it, there's another instruction called a return. And that's going to magically bring us back to wherever we were when we called the subroutine. Okay? So this is more advanced than a regular jump because we've got to somehow remember where we were coming from and be able to get back there. So call and return in different assembly languages, they'll have different names. You might see jump to subroutine, for example, and return from subroutine, or you might see them called call and return. That's 6502 version, that's x86 version. x86 is your Intel or AMD desktop machine that you probably have today. So the difficulty of this is how you get back. Okay, jumping around in the code is easy. Getting back to where you came from is the hard part. So particularly you need to know where it was that you came from. Okay? You've got to remember where the program counter was here and then be able to restore that in a reliable way. If you look at early high-level languages, like very early forms of BASIC, for example, you'll see they were limited that you could only call one procedure at a time. So in modern languages that you're used to, you can jump inside a function or a method, whatever you call it. It's very common to go inside a function and then that function calls another function, and that function calls another function. And maybe a function could even call itself. Now, in the first high-level languages, that was not possible because the return address, that's the state of the program counter when you make the call. The return address just used to be stored in one fixed location. So you can choose where that's going to be. You might, for example, use a particular register in the CPU. You might design the architecture of the CPU to have a dedicated register that is used for storing return addresses. And those call and return instructions might automatically hit on that register. Or you might decide to have a special address in memory that is used for this purpose. You say whenever there's a call or a return, go and hit on this memory location and store the current state of the program counter. So I'm currently on line 31. I'm going to go and store the number 31 either in a register or in a memory address. Then I'm going to go and jump down here. And when I see return, I'm going to look in that register or I'm going to look in that memory address, and that's going to tell me where to get back. So the problem with that is that it only works once, right? If I call a function and I store where I'm coming from, I store this line 31 in that location. If that function then calls another function, what's going to happen? It's going to go and clobber that piece of information, right? It's going to store the address where it makes the call from, and we've lost the history. That's called the call stack. Yeah, we've lost the history of any other calls we might have made. And so that's why early languages only let you go into one procedure at a time, and then you had to come back before you could call the next one. So a somewhat more advanced version of this that you might see in some workshop examples is using a special address mixed with the subroutine's code. Okay? So an improvement over a fixed location is that each subroutine might have a special address, such as the first address within the subroutine. You might take this little area of memory here, and you might have a convention that says this is where we're going to store the program counter state. So that means when I get to line 31 of this program, and I'm going to go and call that subroutine, I'll take the number 31, that's the current state of my program counter. I'll take my program counter and I'll write it into a memory location here. So this is a map of memory. Yeah? I'm going to write it somewhere in the subroutine, typically the first line of the subroutine. And when the subroutine gets to the end, it knows where to look. It can say, go and look at the beginning of my own code, and that's containing the number 31. That tells me where to jump to get back to the main program. So this style is an improvement over a fixed return address storage, because now this subroutine could at least call another subroutine and they'd be able to get back. You could have many subroutines all calling each other, and each one's storing the return address for how to get back. Can anyone see what the limitation of this method is? There's still a limit compared with what we have in modern languages. Yeah. So what happens if a subroutine tries to call itself? Okay. If it calls itself, if we get to a line here, it's going to take its own address and overwrite it there. And then you have that same problem that you've now lost the history. So this is what you see in kind of second generation high-level languages. These are languages that allow procedures to call each other, but they're not allowed to call themselves. That's called recursion. Okay? And recursion is harder to do. So if we want to do that, if we want the full power of recursive function calling or subroutine calling, we're usually going to need some additional architecture level hardware to enable it. So this is an example of improving CPU design in order to enable the language designers to do more powerful stuff with their high-level languages. And you'll often see this. You'll often see the language designers will call the architects and say, could you add this feature, because we really want to do this thing. And it's going to be a lot easier for us if you can put something in the silicon to enable it. And this feature that enables recursive calling is called a stack. So you've probably all come across stacks as a software construct, right? They're a basic data structure. You'll see them in algorithms and data structure. If you haven't seen stacks before, they're the computational equivalent of a physical stack of papers on your desk. Every time you get a task that comes in, actually this is a really bad way to do personal time management. Bad way to manage your time is keep a stack of all the tasks coming in. And every time someone gives you a new task, you put it on the top of the stack. Yeah? And then when you're going to do something, you take the thing off the top of the stack. That's called popping the stack. Putting it on is called a push. Taking it off is called a pop. Every time something comes in, you push it. Every time you want to do something, you pop it. Okay. Why is that a really bad way of doing time management? Yeah. And anything that's made its way to the bottom of the stack is probably going to stay there. Yeah.
Why use a queue then?
Yeah. So probably for task management, you'd want to use a queue instead. Yeah, it's a common problem with ironing baskets in particular, or washing baskets. That stuff gets stuck in the bottom. So not a great way of doing task management, but it is a good way of assisting with these function calls. Okay, we'll see why as we go. So the concept of a stack is we're going to take usually an area of memory, RAM, that's outside the CPU, and we're going to allocate that area of RAM for the stack. If we accidentally fill up all that memory, that's a certain kind of error called a stack overflow. Okay? There's a famous website called Stack Overflow where people go for debugging. Well, it's where they used to go before we trained a bunch of AI to look up Stack Overflow for us. But a original Stack Overflow is an error where your stack is full. So the stack itself is going to live in RAM, but we're going to extend our CPU architecture to be able to work specifically with that stack. So in particular, we will create an extra register inside the CPU. We're going to call this a stack pointer. So we might already have an accumulator, we might have some user registers, we've got an instruction register, we've got a program counter. We're going to add the stack pointer to our set of system registers. And the stack pointer is going to work alongside this memory, and it's going to work alongside the instruction set to enable those instructions. And roughly it's going to have two instructions called push and pop. When an assembly language or machine code instruction says to do a push, it's going to do two things. It's going to take the piece of data being pushed, it's going to write it into that area of RAM. And the second thing it's going to do is it's going to update the stack pointer. And the stack pointer keeps track of how much of this RAM are we using. It's going to keep track of what is this address at the top of the stack. If we want to pop from the stack, we will then do the opposite. There'll be another CPU instruction called pop, Pop will look at the stack pointer, it will go and hit on RAM and retrieve whatever was at that location in RAM. It will bring it back and do something with it, typically dunk it into a user register, maybe dunk it into an accumulator if we run an accumulator architecture, and then it will decrement the stack pointer so that now we're pointing at the next item on the stack. So this feature was added specifically to enable proper subroutine calls and specifically to enable recursive subroutine calls. So the idea then is whenever you hit a call instruction, instead of saving your program counter locally or even inside the function, you will push the current program counter onto the stack. Okay, so when you get a call instruction, that is typically going to go and effectively it's going to call that push instruction. So usually if you have an architecture with call and return, it will also have push and pop because it has a stack architecture that's been implemented. So call is going to go and push the program counter onto the stack. Then you can run your subroutine, and that could include calling other subroutines, and each of those is going to push their program counter on the stack. And so when you use a debugger and you see that the call stack, yeah, it's still called the call stack in a high-level language. You see all the different functions that were called leading up to where your error is. The way you can see that in the debugger is because all those addresses have been pushed on the stack, and you can go and look at that stack and see how your program managed to get into the stack. So every time you get a return statement, it's going to pop from the stack, it's going to put that into your program counter, and then execution will resume from wherever you came from. Once you've put this into your architecture, you'll find users will then go and find their own uses of it. This often happens in architecture. You design a CPU feature for one purpose, like enabling subroutine calls, but you'll find users, especially users of a hackerish persuasion, will then try and exploit the feature and do new clever things with it. So in particular, in some architectures, this stuff is deliberately hidden away from the user. In those architectures, you won't get a push and pop instruction, you'll only get the call and return instructions. In other architectures, it's deliberately left open for the user, and so they can do call and return, but they can also do push and pop. Now, if you're programming against one of those architectures, you've got to be really careful, because remember, the system itself is relying on the stack to do calls and returns. Yeah. So this is a basic thing that users might want to do. If they're used to putting things in loads of registers, some assembly programmers like to use lots of registers, right? Well, nowadays it's compiler writers who do this rather than end programmers. So if you like that kind of programming and you don't like putting stuff in RAM all the time, you might just start using the stack as another data store, and you might develop this programming style where you're constantly pushing and popping stuff off the stack. Yeah. So that's fine as long as you respect the subroutine structure, because if you push a load of stuff on the stack and then someone does a return, then you're going to be in trouble. Yeah. So you're giving the user a lot of responsibility. You're giving them a lot of power, but you're giving them responsibility. What you tend to find in practice nowadays is it's the compiler writers who make use of this, and they'll use the stack, they'll use it to do extended function calls. So when you call a function in most languages, you expect to give a bunch of arguments, yeah, or parameters. So usually the people who write compilers will have a convention that if you call a function with 5 parameters, first they're going to push the program counter on the stack. That lets you get back. Then they might push the number 5 on the stack. That says this function has 5 arguments. And then they push the 5 arguments on the stack. And then they do the actual jump to get inside the function. So usually the stack is used as a way not only of going inside a function, but also keeping track of all the arguments that have been passed to it. That's a major place where different compiler writers disagree and fall out. If you've ever tried to combine libraries that are written with different compilers, for example, you can get into a lot of trouble because one compiler might have a convention that you put the program counter, then the 5 arguments. The other one might say we're going to push the 5 arguments first, and then the program counter. Or another one might say we're going to push the number 5, and then the arguments, then the program counter. And so this is why it's difficult to link libraries together that have been created by different people. It's why usually when you build a big system, you've got to download the source yourself and make sure that it's all compiled with the same compiler. So here's what it can look like in practice. Here's a C++ program. Okay, we've got a main function. We've got a squaring function, right? Power of 2 function. This takes an input argument and it times itself. Your compiler is going to convert that into something like this. Okay, this is a 6502 example. Nice human readable assembly language. So you can see, here's the main function. This is going to call the power function. It's doing a jump to subroutine. That tells us to jump up here. But as we do that jump, we're going to push the program counter onto the stack. And so, in this case, there's an argument as well. So we're also going to push that argument on the stack. When we get inside the function, the compiler has put in an instruction to retrieve the argument. Okay, so we push this thing on the stack here. Okay, that stands for push accumulator. Whatever's in the accumulator goes on the stack. Now we call the function. When we're inside the function, we're going to pop from the stack. We get the argument back. We do our maths on it. Now you've got to decide how you're going to return the result as well. So you might return the result on the stack, or you might return the result in the accumulator. In this case, we're returning it in the accumulator. When we do the return from subroutine, that's going to pull the return address off the stack, and it's going to send us back to where we were in the main code that called out to the subroutine. The 6502 did not have a hardware multiplication instruction. You'd have to write that yourself by doing a bunch of additions in a row, for example. Now, another feature that the software people called the architects to add is called an interrupt request. This is the ability to interrupt a program that is currently running. Okay? So say you've written your Space Invaders game, the user is playing it quite happily, but your computer would like to do something else. You know, you're running a web server in the background, and someone's dialed into your server, and you now need to go and deal with that request and send them some HTML. And ideally, you want to do this in a way that the programmer of Space Invaders does not have to worry about or think about. So later in your studies, you will learn about operating systems. Okay, operating systems are programs like Microsoft Windows or macOS or Linux or FreeBSD. They're the programs that take over your whole computer shortly after you've turned it on, and they then enable multiple other programs to run simultaneously, or at least giving the illusion that they're running simultaneously. So for example, you might have a desktop open, you might have a word processor and a web browser and a database. They're all running together. And the people who program those applications don't have to worry about the other applications. The operating system provides this illusion that they've each got a completely clean machine to run on. The way operating systems do that is by using these interrupt requests. An operating system at its core has a timer. It waits for the timer to go off, and then it says, go and run the word processor. You know, 5 milliseconds, put the word processor program on the CPU. At the end of that 5 milliseconds, the timer's going to go off again. You're going to send this interrupt, and the interrupt is a physical wire going into the CPU. Right? This is the pin out of the 6502. You can see there's a physical metal pin with a physical wire called IRQ for interrupt request. So this is a lowest level architectural feature, right? You're going to let this thing run for 5 milliseconds. When the timer goes off again, you put a physical voltage on this IRQ line, and that says stop running whatever you're doing. Do something to save the state of whatever you're doing so you can come back to it. That's usually the hard part. And then go and run something else. And typically that's the operating system. This is how you run Linux or Windows or macOS. For 5 milliseconds you're running the word processor, the timer goes off, then it says go and run a bit of the Linux code, or run a bit of the Windows code. And then that decides which program is going to run next. Before we put this in at the architecture level, there was a generation of operating systems that relied on programs being nice to each other. It's called non-preemptive operating system. So if you used the early ARM1 based Acorn Archimedes, for example, this was the beginning of the ARM architecture. There was no IRQ system in the operating system. And so everyone writing programs on the Archimedes had to be nice. You assumed that whoever wrote the word processor was going to write a loop that says, do this stuff for 5 milliseconds and then call this special function in the operating system to let the operating system have a go and to let it go and call any other program. And that worked great until any one program forgot to do it. So if you downloaded some little Minesweeper game, tiny little app sitting on your desktop, and the programmer had forgotten to call the operating system, or had chosen not to call the operating system, that program could then just take over the whole machine because there was no way of getting back to the kernel of the operating system. So by adding these IRQ lines, it takes the responsibility away from the programmers, and it ensures that whoever writes the operating system has the ability to tell the CPU to switch on to doing something else. So the way this is typically implemented is you get a physical pin, physical bit of wire, and this presents all kinds of interesting security applications, right? If you want to interrupt someone else's CPU, you might consider soldering a bit of wire onto that pin and sending a high voltage to try and convince it to stop doing whatever it's doing and have it do whatever you want it to be doing. You put a high voltage on it, and that's going to put it into interrupt mode. The architecture then has to decide what to do next. Okay, and usually this is done by having a special register. Maybe you might have another register in the CPU that stores an address. And the idea is whenever the interrupt goes off, you're going to update the program counter with whatever's in that address. Okay, so the user's going to say, here's the address of the Linux kernel. Every time I get an IRQ, set your program counter to go and call the Linux kernel, and that switches you into the other mode. The harder part of it is what do you do with the program that was currently running, because that program's got its own area of memory, it's got stuff in the registers. At that point, the operating system needs to do a whole load of work. It needs to somehow save a copy of all that state. Usually that's done at the software level still, rather than the hardware level. And try and implement the minimum amount of architecture to enable the software people to do their stuff without completely taking over everything they do. The other place these things tend to get used is with devices. We'll talk about input-output I/O later on, and we're going to rely on IRQs. When your print job has finished, you'd like your printer to call you back and say, hey, I just finished this thing, would you like to go and run a program that prints a message on the screen? So we'll be relying on IRQs later on. The operating system people were also very keen to ask architects to put in some security features. So even if you can't take over the whole machine by not returning control to the OS, there are still other very bad things you could do. As soon as you're running on this multi-program operating system environment, all kinds of security issues come along. So in particular, it's really not a great idea to allow one user to just load from memory that is being used by another person's program. Yeah, you might have the web browser open, it's using this chunk of RAM, and your online banking password is stored at this memory location. You really don't want arbitrary other programs to come along and start loading from the address that contains the user's online banking password, right? You'd like to enforce separation between programs by saying some programs only have access to certain parts of memory. So again, most of this is handled by the operating system. You'll learn a lot more about this when you do the operating systems module. But in order to understand operating systems module, you need to understand what is provided by the architecture, because they're going to rely on it. And so most modern CPUs will have some hardware feature that at minimum keeps track of two modes called privileged and restricted. So some architectures will make this very complex with different levels of privilege. Most basically, you'll have two forms of privilege mode. If you're in privileged, this is intended only for the operating system program. In privileged mode, you can do anything. You can load and store anywhere in RAM. You can fetch from anywhere in RAM. You can access all the hardware devices. You have full power over the machine, as in an older CPU, where this is the default setting anyway. So in addition to that, modern CPUs will give you this restricted mode. So you're probably going to have a flag or a register somewhere in your CPU that just keeps track of which mode am I in. That could just be one bit. It could be a single flip-flop saying, am I in 1 for privileged and 0 for restricted mode? And when you're in restricted mode, that's going to prohibit you from doing certain things. So we're going to put in hardware-level digital logic that makes certain tests and prevents certain things from happening. Okay? And typically, that's going to be a test of which memory is the user trying to access. If a user program makes a load or a store instruction, restricted mode is going to make some comparison of those addresses with usually information given by the operating system. And if that program's not allowed to load and store in a part of memory, then you're going to raise an error. That's called a segmentation fault. Okay? You might have come across segmentation fault errors. Segmentation fault means you're trying to access a piece of memory that you're not allowed in, a segment of memory. So a typical modern CPU is going to look something like this, right? We're going to combine these access modes with the IRQ system. So there's going to be a timer built into the CPU. That timer will go off every few nanoseconds, probably nowadays. Every few nanoseconds, the timer goes off, it puts the voltage high on that wire. That's done automatically outside the rest of the CPU cycle. That gives you the callback. It's going to set your program counter to the address of the operating system. It's going to kick us into privilege mode. It's going to let the operating system do its own thing, all the stuff that you will learn about later in your operating systems module. And at some point, the operating system will stop running and it will set the program counter to the address of one of the programs that are currently running on it. And it will set the CPU into restricted mode to stop that program accessing memory belonging to other programs.
We need supervision. Maybe
Let's talk a little bit about the life of an architect, or the life of an instruction set designer. Most people who work in architecture don't get to do this. Most people, if you get a graduate job in architecture, it will almost certainly be at ARM, and it will almost certainly be testing other people's architectural design. It's relatively easy to invent an architecture. I drew that Manchester on the back of an envelope in a boring meeting, but we spent much more time after that verifying it and getting all the bugs out. And so if you go to work for ARM, that's probably what you're going to be doing, right? Some much more senior person will have designed the architecture, and that only happens every few years or decades even. And everyone else is involved in making the thing actually work. So if you ever do become a rock star architect and you're involved in doing the architectural design, these are some of the issues you have to think about. And fundamentally, an instruction set, that's the collection of all the instructions. You have the definition of the assembly language or the machine code that the CPU can execute. An instruction set is a compromise. It's an interface between what you're showing to the users, which in the olden days were human programmers writing in assembly language. Nowadays, they're usually compiler writers. Those people have certain needs, things they want to see in the interface, in the instruction set. And you're compromising that with what your architects are able to deliver. Okay? So the life of an instruction set designer is this fight between users coming in on the phone and saying, could you add this thing for us? We'd really like an instruction that implements this cryptographic primitive, or can we have some deep learning instructions for building this year's transformers out of. And then on the other hand, you've got your architects coming in saying, we really don't want to make that. That's not how our digital logic works. Here's something we could do. Look, we could make this really cool exponential instruction, or we could make this new security feature. This is all stuff that the logic we have really lends itself to. And the instruction set designer sits in the middle of that, trying to make a compromise between what the users want and what the architects are able to deliver and implement efficiently. So often these people will be in the same building now. If you go and work for ARM, you'll probably find ARM has a bunch of compiler writers in-house whose job is to make languages like C++ go as fast as possible for the architecture being developed. And so those people will sit down together and they'll try and come up with this compromise. This is where you'll hear the word architecture used in a slightly different way. Here we use architecture to mean everything in the module. If you hear people talk about an architecture, if you use architecture as a noun, they're typically talking about the instruction set. So you'll hear about instruction set architectures. That's the user-facing definition of what a CPU can do. So you'll hear about the AMD 64 architecture, right, with the Blackwell GPU architecture. So if you're sitting in the middle of this process, you have to think clearly about what the CPU has to do. What are you specifying the requirements? So most programmers will want some sort of arithmetic. Some programmers will want really specialist arithmetic. That might involve floating point, involve really specific mathematical functions, especially for multimedia codecs or for cryptography in particular. You need to think about fundamentally how the data is moving around. So the CPU can do stuff on its registers internally. Once you've got data in, you've got to think about how do I move data in and out between the CPU and the memory. And when we talk about input-output later on, you've also got to think about how do we move data between the CPU and your I/O devices. And you've got to think about these program control instructions. Do I want to have just basic jumps? Do I want to have conditional stuff? What kinds of conditions? Do I just want to test if things are zero? Do I want to branch on other kinds of conditions? Especially conditions to do with errors and exceptions. Do I want to put an error handling system into the architecture level? Do I want to add stuff for subroutines or for any other kind of more advanced program flow control? And you're constantly thinking about where should the data go? Do I want to have lots of registers in my CPU? So some programmers and compiler writers like to have lots of user registers available, and they're going to bring everything into CPU initially, and they're going to do all their computation inside of CPU, and only when it's done are they going to write the result back to RAM again. In other architectures, you only have a couple of registers, and so the programmer is going to have to constantly be bringing stuff in and out of the CPU, which is a much easier life for the architects, but it's a much harder life for the users, or for the compiler writers. And there's often decisions around what goes into an instruction. You'll see different instruction sets will have very different operands. If you're working on an accumulator architecture, usually you only need one operand, because it's obvious that everything is getting done in the accumulator. You're going to add a number to whatever's in the accumulator, you're going to put the result there, there's only one operand. Other architectures to do addition might have three operands. You might say, take this information from here and this other number from here and add them together and store the result in a third place over here. And you've got to think about all the stuff from our data representation lecture, right? How is arithmetic going to work? Do you want integers? Do you want natural numbers? Do you want floating point numbers? Do you want 2's complement? Do you want some other representation? These all go into the architect's decision. You can usually cluster types of instruction into these four headings. So if you look at the instruction set of a real CPU, these will probably be the titles of book chapters or even book volume names, because modern instruction sets have got very big. Fundamentally, you have instructions to do with getting stuff in and out of the CPU. So these are loads and stores, maybe other kinds of memory access like the stacks we saw. Similarly, getting stuff to I/O. Some architectures will have dedicated instructions for doing I/O. Other architectures make I/O appear as if it's a part of memory. We'll look at these processes in later lectures. But you'll see fundamentally some architectures deal with I/O and other ones don't. They push the problem outside and make it into the I/O designer's problem. You've got data processing. This is the actual work of the CPU, right? Like arithmetic. What kind of operations do you provide and what kind of control structures do we provide? How we do operands is one of the major ways that architectures appear differently to the user programmer. So let's consider a really simple instruction, right? We want to add two numbers together. So in this case, we're going to make A equal to whatever it was before plus something else, B. Here are at least 4 different ways we could do that, okay? In this version, this is our instruction. Yeah, these are the zeros and ones. And we're going to split that set of zeros and ones into several pieces. Remember, there's an opcode that says we're doing some adding. So you've got binary code for adding. What do we put in the operand? Well, one way of doing it is to assume that the user has already done all their loading. We've already got 2 registers inside the CPU, and we assume the user's already filled them with the number 3 and the number 7, and now we want to add the registers together to get the result. And notice here we don't specify where the result goes, yeah? So there's a common convention that you put the result in the first register. That means we're going to overwrite whatever was in the first register. Another way of doing this is to have 3 operands, and one of them could say which register does the result go in. But in this style, this is associated with RISC style architectures, by the way. In this style, you assume the data is already in CPU and the arithmetic just acts on the registers. This is a different style, usually associated with CISC, where you are adding one register to a piece of data that is not in the CPU, it's stored in memory. Okay? So this is a more complicated instruction, because to do this is roughly how the Manchester Baby works with its subtract operation. To do this, you've actually go out and you've got to hit on the RAM and effectively do a load from RAM, all as part of the same instruction, and then do the arithmetic, and then put the result somewhere. So in the Baby, you only have one user register, that's the accumulator, but you have this form of addition. Here's another way of doing addition. You're saying, take whatever's in register A and add an actual number to it. In this case, the number 32 has been included in the opcode, and we're just going to add that number 32 directly into the register. So we're not loading this number from anywhere else. It's a constant that appears in the user's program. Or you might want to do this. This is not initially obvious why you'd want to do this. It turns out to be very, very useful. This is called indirect addressing. And in this kind of instruction, we've got data already in a register. We're going to give it an address in the opcode. That address does not contain the second number to add. That address contains another address. Okay? So in indirect addressing, we might give it address 50. This means go and look in address 50 and expect it to contain another address. It might contain address 39. So the instruction says, then go and look up that address and load the data from there and go and add it into whatever's in data register 2. Yeah? This sounds like an incredibly convoluted thing to do. The reason this is useful is because the high-level language people, specifically C-style languages, like to have this feature called pointers. Okay? And if you've ever programmed in a C-style language, you can have a variable that contains an address. That's called a pointer. And it's really common in those languages to throw pointers around and to do arithmetic on pointers and then to dereference a pointer by going and following up what's in the pointer. And so this indirect form of addressing, you can see this instruction gets a different name because it's actually doing a different mathematical operation. Indirect addressing is one of these features that's come along when the language designers call the architects and say, look, we've got this new feature in the language, we want to do this stuff with pointers. It would really help us out if you could add a whole load of extra silicon to do this in a single instruction. It'll make all our C programs run faster. And in this case, the architects have given in to the language designers and said, yeah, you can have your extra feature. We'll put in another chunk of digital logic occupying space on our silicon just to let you do this thing that you'd really like to have. If you're working in accumulator architectures, the instruction set is usually much simpler. So this is why we tend to give you accumulator architectures in the workshops and in the Manchester Baby example. In a pure accumulator architecture, there's only one user register, and that makes all the instructions much simpler because you know where one of the arguments is coming from. So most instructions in accumulator architectures will only have one operand. It's assumed that the other operand comes from the accumulator, and it's assumed that the result of the calculation will also be stored in the accumulator. So if you run an accumulator architecture like the Manchester Baby, arithmetic will look like this. It'll say, for example, add. Okay, the baby only has subtract. If you've got one with an adder, it'll say add, and there's a single memory location, right? And this means take whatever's in the accumulator, go out and get the data from this memory address and add it into the accumulator so that the accumulator gets updated, and you only need one operand to do that. If you're used to using handheld calculators, handheld calculators are usually accumulator style. If you type +5, it means update the accumulator by adding 5 to it. Yeah? Take whatever you've already got and make this change and keep that as the running total in it all. Or it's common for architects to give you an accumulator but other user registers as well. So the 6502, for example, has 2 user registers called X and Y, and then it's got an accumulator as well called A. If you have that kind of architecture, usually the assumption is the results are going to go in the accumulator, and you might do things like this. You might say add register 1 to register 2, and you don't have to specify where the result goes because that's what the accumulator is for. Or you might have this kind of addition, and you might have another version of addition that only takes one input, and it's assumed that the second input is coming from the accumulator. So when instruction design started, it was very simple, right? This is the complete instruction set for the Manchester Baby. This is what we built last week in the Logisim example. So this is a really minimal instruction set, right? This is an important instruction, halt. This tells the program when it's finished. We can do a load, we can do store, we can do subtract, arithmetic. You've got a jump, basic jump, you've got a compare, and remember, compare sets the state of a flag, and that enables you to then do conditional jump, and to either skip over a line or jump to another location. This is the 6502 instruction set. You can see this is much bigger than the Baby. Okay? Here you've got a byte's worth of opcode. So in theory you could have up to 256 instructions. Not all of them are used, but you'll see the 6502, it's got loads and stores. You can load and store from different registers called X, Y, and Z. You can do subroutines. You'll see there's a jump to subroutine. There's a return from subroutine sitting over here. You've got lots of arithmetic operations. You can do logical operations, anding and oring. You can do addition. You can do subtraction. You can do shifts, bit rotations. That's an example of a somewhat larger architecture. You might decide to put floating point in your architecture. So we talked about integers. We've seen how to build an integer ALU. I'm not going to show you how to build a floating point arithmetic unit because they're really hard. Floating point is very difficult to get right in digital logic, and it's a major source of errors, including the famous $500 million Intel loss in 1994 when they messed up the design of the floating point unit. But lots of things to think about if you're going to add floating point into your architecture. Right, let's stop there for lunch. When we come back, we'll talk about instruction level parallelism, and we'll talk about the risk phase. See you after lunch.
I'm just gonna start gambling.
They're very good at
Quickly.
No, just